Okay. In our previous session, we have studied this dynamic scheduling mechanisms of how different subscribers would get the resources when they're all fighting for the resources. And we have studied that there are multiple scheduling algorithms that are in play. Each one will be taking care of different aspects. And the final one we have studied is related to this token queue mechanism, where based on the promised data rate, a token bucket would be maintained for each flow, typically for a subscriber or a subscriber's particular flow. And if you are using up all the tokens, uh, then it is good. But whatever the extra you demand on top of the promised data rate, typically you would be given less priority for that. So the more tokens you have in the bucket, the more preference you will get because the VA of T value would be higher. So we have studied how this token queue mechanism works. But all these things are dynamic scheduling mechanisms. So how to dynamically schedule the resources? Uh, but let us go to one particular slide that we have studied earlier. So we kind of have to revisit to understand some issues with the dynamic scheduling. So that is this one, GBR and PBR. So we have this concept called as a guaranteed bit rate, which is kind of divided into PBR and BSD. So every by BSD time, you have to send PBR amount of traffic. Ultimately, that will make you achieve GBR. Okay. Now I'm going to ask you a question. Try to participate. What happens if the BSD value is too small? Is there any problem that you see if the BSD value is too small, or when it is becoming smaller and smaller, the BSD, bucket size duration? Now I'm asking from the point of view of dynamic scheduling. Uh, what is the issue if BSD value is very small value, bucket size duration? Anyone? Anyone wanted to comment on it? I need at least two participations. Please go ahead. Let us do it that way. I'm asking you the question. Listen carefully. What is the problem if the BSD value is too small, or BSD value is small? Your bucket size duration is small. For example, let us take that BSD is 10 milliseconds. What is the issue if it is 10 milliseconds? And what is the advantage if the BSD is very big, like 1000 milliseconds? Number of chances to send the data will decrease. That is the same point I have made yesterday. GBR will increase. That is utter wrong. GBR will never increase if the BSD is small. If you take a look at it, the table is in front of you, which proves the otherwise, right? Like irrespective of whatever is the BSD value, because your PBR, we are kind of matching it to that BSD, our achievable guaranteed bitrate is the same. So that's a wrong idea. GBR will never increase. That's not a problem. First of all, GBR will never increase, and it is not a problem. Eh, Okay. If BSD is small, then in dynamic resource allocation might be a chance for packet loss. How? How is that, Rohan? In dynamic resource allocation, how there is a possibility for losing the packet? Rahul, scheduling possibility is decreasing with decrease in BSD. Yeah, that is correct. That is the same point we have made yesterday. but I am actually looking for a new point here. Number of scheduling possibilities would be less if the BSD is small. That's good. That is in front of you. Again, this table is telling you that. All right. Okay. I'm not getting any further answers. So let us continue. First of all, whenever you are performing this dynamic resource schedulings, uh, the important point is the scheduler will have to schedule the resources and send that information on a channel called as PDCCH in the form of something called as DCI, downlink control information. Now, this is where we get the problem. If a user require resources repeatedly, like every 10 milliseconds once, because the application is demanding a lower BSD value, every 10 milliseconds once it would like to send or receive the traffic, you need to schedule the resources for that particular application data stream or for our logical channel data stream every 10 milliseconds once. Point, every 10 milliseconds once you have to schedule the resources for that particular data stream and convey that information to the mobile in the form of DCI, downlink control information. What is the trouble in it? Obviously, if you schedule it, you have to provide this information. Very good. How that is a trouble? If you remember, the PDCCH size, the size of the PDCCH is dynamic. You can actually either reserve, one symbol or two symbols or three symbols in your at the starting of the slot for PDCCH operation. But on what basis this size would be typically determined? If you have to pack more and more DCI data, downlink control information, which is carrying the scheduling details, you have to reserve a bigger size for PDCCH. The problem if you reserve bigger size for PDCCH is it will be kind of wasting the resources or consuming more resources. Actually, these two channels are, you know, kind of opposite channels, PDCCH and PDSCH. If you reserve more resources for PDCCH, uh, PDSCH resources will go down because both of them are actually present in the same slot. Whatever the resources that are not already allocated for common channels, only those resources could be used by PDSCH channel. So if PDCCH is demanding more resources, definitely PDSCH size will reduce. And opposite is also true. If the number of resources we are using up for PDCCH reduces, your PDSCH size will increase. Basically, if your PDCH size increases, you will be able to send more data for the subscribers in the downlink for the mobiles. So that is an advantageous position. You always wanted to have more resources available for PDSCH operation, more number of symbols being used for PDSCH. You kind of want that. But if you have to dynamically require to reserve the resources for subscriber and convey the information to those subscribers every 10 milliseconds once, if there are a lot of such mobiles are there present uh, who are operational in the cell, and to send their resource information, you require to definitely use up lot of symbols, or you have to use very huge amount of resources for PDCCH to carry the DCI, the downlink control information. because each user typically requires a CCE, control channel element. If more control channel elements, bigger size for PDCCH. So they started thinking, hey, anyway, we have to allocate a resource for this subscriber every 10 milliseconds once, because application is kind of a VoIP application or generating the data constantly, voice over IP traffic. Like right now, I'm speaking every 10, maybe every 20, 30 milliseconds once, my computer is converting my voice into a digital data frame and sending it to all of you. Every 20, 30 milliseconds once. Of course, that will be dependent on the coding mechanisms that we use and what kind of a coder we use. The timers will be changing. But most of the times, the applications like VoIP demand that the resources are available at repeated, intervals, one particular repetition period. On the basis of that, they would demand the resources. So you definitely, to carry that information, you need to reserve the resources. But the problem is with the dynamic mechanism. If you reserve the resources dynamically, you need to provide that information to mobile in PDCCH, and that causes issue with DCI sizing being increased or PDCCH size being increased. That will reduce the resources for PDSCH. They wanted to counter this problem. Can anybody give an idea, like what could we do to avoid this? Remember, we cannot avoid allocating the resources to subscribers. That you cannot avoid. But you wanted to avoid these excessive scheduling details that are being sent to the subscribers. So I'm asking about that. So how do we avoid that? Or how do we solve this issue? Come on, participate, guys. At least two or three people participate, please. I'm giving you a challenge. I'm asking you, hey, how can you prevent or how can you reduce these scheduling details that you have to send, especially for these repeated, the subscribers who want repeated resources continuously every 10 milliseconds once. For example, if it is 1000 milliseconds, the problem is not big because you have to send the scheduling information every one time every 1000 milliseconds. Not a big issue. Your DCA is not going to consume a lot of resources. But every 10 milliseconds once for every subscriber, it is too much. Too much of DCA. PDCCH requires a lot of resources. How to avoid this is my question. I'm asking you to come up with some intelligent solution. Anyone? Okay. No answers. That's bad. Great. Anyway, let us continue. Simple idea here is tell the mobile equipment that, hey, anyway, you require the resource every 10 milliseconds once. What do I do is I allocate a resource. I'm giving you that resource related information, but I'm also telling you that the same resource will be repeated for you every 10 milliseconds once, maybe every 20 slots once. Same PRB number, for example, physical resource block number 5 and 6 are allocated for you repeatedly. Every 10 milliseconds once you get that resource, and I don't need to send this information to you in the DCA format every time, not required. So I'm going to avoid that. So that means you are kind of fixing it up, fixing the resource up for quite some time for the subscriber and telling that information duly before the hand, before the actual situation starts. You tell the subscriber the same resource would be repeated for you. You don't need to look up for your details in the DCA information, whether your RNTA is present or not. Kind of, we can kind of avoid that. This is called as semi-persistent scheduling, or it is not dynamic scheduling. The resources are kind of reserved in a semi-static manner. The same resource is getting repeated for these kind of subscribers. But which subscribers need to move into this semi-persistent scheduling? Do we have to have this approach, used for every subscriber? No, we have to fit in the subscribers who require or who are demanding low BSD values. So the scheduling algorithms will have to kind of keep inspecting each and every user's demands and find out if any user who is demanding too low of a BSD, say that, hey, this guy is demanding too low of a BSD. If you keep him on dynamic resource allocation, we have to convey the resources every time to him. That's kind of wastage of DCA and everything. So we'll pull this guy into semi-persistent scheduling. There is another name for this semi-persistent scheduling in 5G. It was actually called as semi-persistent scheduling in old technologies, but if now it is called as configured scheduling. Of course, the semi-persistent scheduling word also is reused, plus configured scheduling. Now, what is the advantages with the configured scheduling? Once you reserve a particular resource that is getting repeated for any subscriber, now you can take those subscribers out of your scheduling algorithm. Typically, scheduling algorithms are pretty complex. If you have to consider more and more subscribers, your algorithm will become more complex. Your algorithm will have to uh, what is the complexity with the scheduling algorithm? Let us suppose you are sending the scheduling information or the DCI uh, one time in every slot. Let us suppose. So one slot is zero point 0.5 milliseconds. Now, what is the complexity of the scheduling algorithm? How many number of subscribers the scheduling algorithm is configuring the resources for? Lot of subscribers would be there. By considering all their different inputs, scheduling algorithm will have to come up with a decision every zero point 0.5 milliseconds once, and also it have to convey that information by using the DCI on the PDCCA channel to those subscribers who are waiting for the resources. So the algorithm has got very small amount of time, zero point 0.5 milliseconds. It will have, that's all, not more than that. Because every zero point 0.5 milliseconds, you have a new scheduling TTI. If that is how it is working, if that is how it is configured. So obviously, just imagine a mathematical algorithm completing very complex mathematical algorithm, completing its task in zero point 0.5 milliseconds and and deciding which users must get the job. Zero point 0.5 milliseconds is pretty very small value. Like from human beings' point of view, 1 second is 1,000 milliseconds. Now it is 1 by 2,000 part of a second. Now, the complexity of the scheduling algorithm will increase if more and more subscribers are getting added to the your scheduling into the schedule, what do we call it, scheduling line, for example, scheduling queue. If more subscribers are getting added, now you have to design, if the number of subscribers are too high, you have to design more efficient scheduling algorithm which will be finishing its job in zero point 0.5 milliseconds and deciding the resources for every subscriber that is out there, or not every subscriber, but yet some subscribers can be left out. But you have to decide, you have to make a decision. You need to find out some criteria who need to be left out, to whom you have to provide the resources. So obviously, scheduling algorithm will be encouraging you if you say that I will remove some of the users from the scheduling queues and make your job less complex. Definitely that will say I'm happy that you are doing it for me. So this configured scheduling is kind of reducing the load on the scheduling algorithm, because we already know that these users who are demanding the lower BSD values anyway need to be scheduled every 10 milliseconds or 5 milliseconds once. Why not schedule them in a semi-persistent or repeated manner? So those are the points that come here. If the BSD is smaller, G-Node B faces the scheduling issues. That is what the points I explained you. So how this is solved? What are the technical details behind it? Those are here. If the required BSD is small, G-Node B moves the mobile into semi-persistent scheduling or configured scheduling by allocating a special radio network temporary identifier called CSRNTI, stands for configured scheduling RNTI. Is it required for all the data streams, all type of data streams? Not needed. Only for certain logical channels who qualify for this. For example, real-time voice calls which are demanding the low BSD values. So G-Node B is map, allocate the resources for this, not SPSCRNTA, sorry, this is NLT, CSRNTA on a repetition basis. Like one particular resource, keep getting repeated every X slots for N number of repetitions. The advantage, PDSCH resource saving, nothing but if you can use less resources for PDCCH, that is equal to PDSCH resources will be better. So how this works out in uplink and downlink, what is the perceivable difference between the dynamic scheduling and these configured scheduling? First, we see the dynamic scheduling mechanism uh, in uplink. So this is without configured scheduling. G-Node B, we are considering the mobile equipment is in RRC connected state. Mobile would be monitoring this channel called as PDCCH to find out any resources are allocated against its RNTI. Definitely, it will be looking uh, on PDCCH channel with the help of something called as CRNTI. If it gets any information on the PDCCH, especially DCH00 with CRNTI reservation, or CRNTI is scrambled on the CRC part, your cyclic check, cyclic redundancy check is scrambled with CRNTI, then you know that your resources are scheduled. Uplink resources are scheduled. So obviously you are allowed to use PUSCH because it is been provided with the resources on DCI, and you transmit the uplink data. But what is that K2 and this arrow here? K2 is basically offset time between in which slot you have received the DCI and in which uplink slot you are going to send your uplink data on this PUSCH channel. The time difference between it. For example, we can consider it as 3 slots. It's kind of configured, the kind of details would be provided to the mobile, yeah, as part of its configuration details. What is the size of the K2? But K2 is the difference between when did you receive the downlink, when did you receive resource related information in downlink for uplink channels, nothing but PDCCH, And when are you sending the uplink data? The difference between it. Immediately you won't send it. For example, uh, let us suppose you have 4 slots. Normally in this particular slot, this part of it is your PDCCH, which is containing your scheduling details, uh, DCI. If you get the resources, reserved for you in DCI, immediately you cannot transmit in that same slot itself. You cannot transmit because downloading and decoding this DCA information definitely takes some time for the subscriber. It cannot be completed, for example, in um, 0.01 milliseconds because this entire slot is 0.5 milliseconds. Now you get the PDCCH maybe in the first 1 or 2 slots, which is kind of 1/7 of this whole thing. So obviously, once you receive it, immediately you cannot decode it and start transmitting the data in uplink in the same slot itself. So obviously there will be time gap. Let us suppose if the K2 value is 2, so you have to kind of leave um, 2 slots, the same slot that you received and the next one. So obviously where you will be transmitting your PUSCH is here. If it is 3, you will be transmitting PUSCH here. So whatever the resources that are allocated for you, from the moment you received that resource information, where you have to apply those resources, that is K2. Okay, fine. This operation keeps getting repeated. Now, if it is like if you wanted to find out if your data is received or not in uplink, you have to look for the next DCI and you have to look for NDI, new data indicator. If the new data indicator is toggled or not, you will look into it. If new data indicator tells you that you are allowed to transmit the new data, you can continue with the new data. But if the NDA tells you that the transport block reception is failed, CRC errors occurred, you could not solve the CRC errors, G-node B, so then mobile equipment will have to go for a retransmission if required on the PUSCH by using the newly allocated resources. So this is the acknowledgement mechanism, ARC acknowledgement or negative acknowledgement that happens on your DCI for uplink data. For uplink, you get ACK-NACS in downlink, and based on it, you either transmit original data, fresh data, or new retransmission. This is dynamic scheduling. So you are continuously monitoring PDCCH for finding out which resources are reserved against your CRNTI. But how the configured scheduling works in uplink? Okay, now this configured scheduling, there are 2 types of configured scheduling in 5GMR. And these configured scheduling details are basically provided by RRC. It won't happen at the uh, it would happen with the L3 signaling at RRC signal. RRC has got some role to play. To what degree RRC have to play, that depends on what type of uplink scheduling we are talking about, what type of configured scheduling we are talking about. First one, configured scheduling type 1. Mobile is in RRC connected state. Forget about this downlink data. That is something that is not needed as part of this. Gnode B sends a message to UE that I'm activating CS type 1 configuration. Activation, I'm sending you the resource related details at RRC and what is the periodicity, how much time these resources will be repeated for you, and how often. Like every 10 slots once, the same resource would be allocated for you, or every 20 slots once. For how much time? The same resource would be allocated for. Complete details would be provided by Gnode B to UE. Now UE kind of not required to look for its uplink resources on the PD CCA channel in the form of DCI because it's already provided in a perfect way by the Gnode being. So what does the mobile need to do now? By using those resources that are indicated, you would be transmitting the uplink data on PUSH. But when you are sending it, after you send the data, you have to again monitor PDCCH with the help of the CSRNTA that is allocated to see if your uplink data is successfully transmitted or not. If, to see if the Gnode B is requesting you for any retransmission for this or not. Only for the retransmission purpose, you need to listen to PDCCH. Of course, you don't need to listen to PDCCH continuously. For example, let us suppose the resource is scheduled for you every 40 milliseconds once, repeatedly. Now, in 1 millisecond, in one slot, you transmit the uplink data. Maybe after 2 or 3 slots, you will wait for this, your PDCCH to see if your CSRNTA is being mentioned or not. But if CSRNTA is mentioned and GNODB is sending you that CSRNTA, definitely it is asking for retransmission. Hey, on the repeated resource, you are transmitting the uplink data, but what happened? The data did not got received. So can you please retransmit that particular transport block once again, please? Once
Hi.
it is, yeah,
Sorry to disturb you. This is Sairam from L2T.
yes, I know. Yes, I know.
Have a doubt regarding this, probably the retransmissions point of view. For
Yeah.
example, if we are transmitting probably downlink data with the K2 is equal to 2, and then the TB, I mean, we have given the DCA for the uplink PUSH transmissions. Okay.
Hmm, hmm.
So somehow the packet is nacked. I mean, we are actually not decoded the packet correctly. So what we actually, again, we will send the DCA with, okay, NDI bit will be not toggling, okay,
Hmm,
and then
hmm.
RV will be changing, okay, and then we will be giving the again DCA to UV to request the UV to retransmit it, right?
Yeah. Only if it is a failure, we have to send first of all the DCI for the subscriber. Otherwise,
Correct,
mobile won't even get the DCI on
correct,
its
correct. Actually,
CSR and yeah. Yeah.
based on the next DCA uplink DCA, it will UV comes to know whether this is a kind of the new data or the kind of the retransmitted data
Yeah.
based on that,
In
right?
this case,
So,
there is no chance for new data. It's kind of only if it is retransmitted data, then you will receive a DCI. Otherwise, you won't
correct,
receive a DCI.
correct. So, for example, I mean, assuming that actually if the UV having a SR and all these things, that is a
Hmm.
different story. But assuming that actually if there is a NAC is received, and then actually we have requested again, we have again sent the DCA to transmit the same packet,
Okay.
right? So in this case, is there any possibility that we can change the, along with the RV, can I change the resource allocations?
Resource allocations would be provided. Basically, you cannot use the same resource. This is getting repeated only for every 40 milliseconds once. So this resource, you definitely won't be using that resource because you are doing the retransmission in the middle of these two things, right? You have to
Correct,
use a
correct.
fresh
Not
resource
the
that is
same
indicated
resources.
to you on
My
PDCA.
point is that, yeah, my point here is that, sorry, my point is that not the same exact locations. Point here is that same MCS, same number of PRBs, same the TB size. Is that the only restriction, or I can use the different MCS, or probably, for example, the exact question will be like, so previously I have used MCS2, so that
Yeah.
transmission has got failed.
Hmm.
So suppose we want to take a decision instead of the MCS2, I want to go with MCS0, so that my TB size will be changing and the
Yeah.
corresponding PRBs will be changing.
I don't think MCS. MCS would be dependent on this particular retransmission. MCS would be an overall idea behind your reported CQI, your reported channel quality indicator. So normally when
Correct.
these repeated resources are being provided, what will
Mm.
happen? Definitely for these repeated resources, MCS kind of is required. But how much time you are going to provide these repeated resources, you are kind of estimating that. For example, if the periodicity is for like 500 milliseconds or 10 seconds, so you are kind of estimating that in the next 10 seconds, the CQI is kind of constant for this particular subscriber. By assuming that, that may not be the true, by assuming that it is it is getting it is getting the same CQI from the subscriber. So obviously you would be fixing up one MCS for these repeated resources. Normally when there is a failure, when you are transmitting, obviously that means that there is something wrong went on your in your radio channel conditions. That is why your reception is not successful. When this guy is requesting for the retransmission, it might change the MCS, and it might ask you to go for a lower modulation rate and give you more resources to make this successful. Because we are discussing about a scenario where we are talking about real-time data. Real-time data don't have too much amount of time for retransmissions. You have to kind of complete that very fast. So you GNOD might might be designed in such a way to decrease the MCS, decrease the
No.
MCS, let the
I
mobile.
think sorry to uh,
Yeah,
get disturb in between, but sorry, I forgot your name. I just joined today.
yeah, yeah. Sorry. Yeah,
Okay,
my
what's
name
your
is
name?
Banerjee.
Banerjee. Sorry, Banerjee. Yeah, my
Yeah.
question was probably, yeah, you're right. With respect to the, if you are only relying on the secure reports, but there will
Hmm.
definitely will be a kind of blur also play a role to change the MCS.
Yeah.
So in that case, actually, definitely your MCS will be keep on changing. Suppose if the
Wo-
CQA reports, if CQA
See,
periodicity is,
MCS is not changing. MCS is not changing in this overall periodicity time, is what I'm telling you. MCS is changing only when there is a retransmission required.
mm, okay, probably
You got
my
that?
point is,
See,
yeah,
if there is no retransmission, there is no DCA coming to you, right? You
correct,
won't be
correct.
getting the
I
DCI
agree.
if there is no
I,
retransmission. If you are
mm,
retransmitting means what? The previously transmitted block has been failed. Okay, why it is failed? Definitely due to radio conditions. You could not retrieve that even with the coded information,
correct,
coding information. So that means
correct.
GNODB can decide, hey, these guys' conditions are not so good as the previous CQA have considered, and
Mm,
I'm going to ask him for the retransmission. Let me better go for a lower MCS rate and increase the number of resources so that it can fit the data block into that number of PRBs. So you might have to reserve more PRBs to make him send the data, more resources to make him send the data. You got it?
okay.
If too many
That's so you
retransmissions are occurring, if too many retransmissions are occurring, the dynamic decision the algorithm can take is, I think
mm,
the CQI might have been completely changed. I will go and send another CS type 1 configuration message to the mobile equipment, asking him that, hey, I'm changing your configured scheduling once again. And this time what I'm going to do is I'm asking you to use another MCS. Your previous MCS is not working out. I'm changing the MCS. I'm giving you a new MCS and new set of resources to do the to do the transmissions at a repeated interval. So based on the CQI values, you can keep on changing this CS type 1 configuration on the based on the live situation. You got it?
CS type. CS type means what? What is that CS type? Channel state
I'll
information.
explain. Yeah.
Channel state part.
I did not get that question.
No. CS
Sorry.
type means actually you're talking about the channel state.
No. CS stands for configured scheduling. Type 1, type 2. Configured scheduling type 1, configured scheduling type 2.
Okay.
Two types of configured schedulings are there.
Okay. So finally, my question is actually, I hope actually my question was regarding the uplink scheduling when we were talking about. My
Hmm.
question was if there is a retransmission happening. So
Yeah.
during that time in the DCI,
Hmm.
generally, suppose if I'm changing the MCS from 2 to 0,
Okay.
okay, so will that actually create any problem with respect to the soft combining or not?
Definitely create a issue, but you cannot do as it is the soft combining, because the retransmission is not the same as the previous one. But
Exactly.
uh,
Mm,
you cannot take arc related things into consideration here, because the failure occurred because of your radio situation. This is not a problem only at this retransmission. The soft combining problem will be there every time when you are retransmitting, and if network decided to dynamically change your MCS value when you are retransmitting. So that time also it will occur. So that is not particularly applicable only in this case of configured scheduling.
okay. So you mean to say that to get only the changing parameter will be the
Changing parameter will be,
RV, redundancy version,
yeah, uh, typically.
typically. Okay. Okay, Banerjee, thank you. I hope.
Okay. So you'll keep looking for the uh, retransmission, and complete this number of times and the periodicity. So this is CS type 1. Whereas in CS type 2, the resource related details won't be sent at RRC level. It only does the CS type 2 configuration, but what resources are getting allocated for the subscriber, for finding out those that resource related details, mobile will have to look on this channel called as PDCCH with its CS RNTI. So it will have to look for the DCI scrambled with the CS RNTI or not. And if it once it finds out that information, then uh, it'll get activated. The CSR and TSCS activation would be done. In the PDCCH itself, in the DCA information itself, you will be known about which resources you have to use for for this particular configured scheduling. Two ways of providing the configured scheduling related details. One is in the RRC level details. The second one is at DCA level. Uh, in your PDCCH channel itself, you would be using. But other than that difference, there is no difference between the configured scheduling concepts, either in CS type 1 or CS type 2. They kind of remain same.
Yeah, I think use cases would be better, right, Banerjee? Where exactly we will use the CS type 1 and where exactly we will be using the CS type 2. Use case point of view, it will be better to understand, right?
I did not include the use cases in here. If possible, I'll add that details at RRC level. Okay.
Okay. Mm.
Yeah.
Yeah, at least probably you can give the SPS as an example. Semi
I'll add
persistent
that
schedule.
at RRC level. Use
Okay.
case related things.
Mm.
I won't go without the slides for that.
Okay, Banerjee.
Now we have the uh, downlink scheduling dynamic. So without the CS, just like the previous scenario, we have this mechanism where you have to keep monitoring the PDCCA channel, and you have the DCA 10, and obviously you have this CRNTA based scheduling. Here we have two K values, K0 and K1. Once you receive the resources, you have to wait for K0 amount of time, and then you will be receiving the downlink data on the PDSCH after K0 time. And after you receive the data after K0 units of or slots of time, you will be transmitting your acknowledgements or negative acknowledgement after K1 amount of time. So on the PUSCH or PUCCH, if you are masking the bits in PUSCH, you would do it. Otherwise, if you send it on, if you want to directly send it in the form of UCA, you will use PUCCH for that. And this kind of keep getting repeated, where your resources will be, you have to look for the resources on PDCCH, the scheduling resources. When you get the data on the PDSCH downlink data, download it and send the ACK or NAC after waiting for K1 units of time, the offset amount of time. So this is in case of dynamic scheduling, the normal mechanism as per what we have studied in the DCI. Now in the semi-persistent scheduling, is not called as configured scheduling now in downlink. It is called as semi-persistent scheduling. So same mechanism, you will be first getting this SPS configuration, and a special RNTA would be allocated to the subscriber called as CS RNTA when the mobile equipment is in connected state. But mobile, once that SPS is configured, it will be looking in on this PDCCA channel with its CS RNTA. And again, you will get in DCI, you will get the CSRNTA SPS activation where resource information will be provided, and when you have to activate this semi-persistent scheduling. From the moment it is activated, the same operation will be repeated. You will be kind of getting the resources every X units of time. And after getting the downlink data, you will have to send acknowledgements or negative acknowledgements in uplink based on what happened to your data reception. If it is failed, you send an ACK, otherwise you send a ACK on either PUCCH or you can also mask it along with PUSCH. So this is only one type available in downlink. There are two different mechanisms available in uplink when it comes to this semi-persistent scheduling. So here the resources are resource information is provided at DCA level. Now this is not dynamic scheduling. This is called as repeated scheduling, or we call it as grant-free scheduling, another wording that is used in 5G. Okay. There is one more technique that they use in 5G NR,
I think
especially
Banerjee,
for the NRT
sorry,
cases. Yeah, sorry. Go ahead.
uh, I just want to ask one team.
Yeah.
Team, why actually we had the two types of scheduling, dynamic scheduling and then SPS scheduling? Actually, Banerjee was explaining, right? Did you get the difference? Why we have the two? What is the benefit over the SPS? What is the benefit over the dynamic? You guys are not asking questions. If you are not asking questions, nobody can help you. Can we assume that you understood?
We came from that point actually at the starting of the session. Did you join from the startings?
No, not at Banerjee.
Yeah,
I just joined.
I have explained that already at the starting of the session. Why do we need it and all the examples related to it, and then from
Okay.
there we'll adhere. Okay.
Okay. So can we assume that?
I'll explain. Huh?
Yeah.
That's why probably they are not asking that question. Yeah.
Okay.
Okay. There is a concept called as TTA bundling in LTE that was got converted or changed in 5G into something called as resource aggregation. What happens in this resource aggregation, or what is this resource aggregation? When do we need it? And first of all, what is the logic behind it? What is the concept? Normally, for the data that doesn't have too much time for retransmissions, so they have decided that even if without even having a negative acknowledgement, also they decided to retransmit the data, either for example 2 times, 4 times, or 8 times based on some aggregation factor that is configured. Now the same data uh, would be repeated, like by utilizing the same resource block continuously for some number of times, 2 times or 4 times or 8 times, either in the downlink direction or in uplink direction. So the idea is, if the data is failed to be received, if there is a CRC error, because there is a repetition that is taking place, you will have more chances to recover that data without CRC errors. You will be able to recover that. Now, the idea is this to be normally used in VONR cases, voice over NR scenarios. This is to solve The problem of the subscribers who are having the low CQI, who are at the sale edge, to improve their service quality, because most of the times if you have a low CQI, there are more possibility for the data failures from the edge of the cell. So you have to kind of keep on repeatedly asking for retransmissions. Now, if you ask for retransmissions, if it is a NRT case, non-real-time services, you have enough time in NRT cases. But RT, real-time services, you don't have that much amount of time. So what do? Because you don't have that much amount of time. You, after attempting for some number of times of retransmission, so you will kind of consider it as a failure, and you continue without the data. So that kind of is not a good for the service point of view. So if they wanted to improve the service, so they can go for this. So instead of having the uh, yeah, having these retransmissions and dealing with the CRC errors and reporting it with ACNACs, you can ask the mobile that, hey, please repeat the same data, for example, 4 times in uplink direction, or I will send you the data 4 times in downlink direction, the same data I would send you. But this is not required for NRT services, non-real-time services. This is required only for view NR services, this concept. It works on the basis of configuration, especially for the subscribers who are reporting low CQI. It is dynamically decided by the scheduling algorithms at Genode B. They would decide it, and they configure this for the subscriber, especially when the subscriber is having this VONR data. Okay. So that is our last concept related to the scheduling parts. More scheduling related things will be covered for us, or the configuration related things would be covered for us in RRC. So we'll look for that at RRC level. Uh, so with that, we are done with this scheduling section. And so far we have covered all the lower layers, especially. Now, as I promised to your team earlier, so I kind of have to introduce to the 3GPP specifications. So for whatever the protocol layers we have studied so far, we will be looking into the protocol specifications, and I'll be introducing the protocol specifications when you have to look for, when you have to study certain things, how to look for it, etc. So first I would start with the physical layer. One by one, I'll take you through these specifications and what exactly you will be able to find out, where you will be able to find out different details. So first we are starting with the physical layer specification 38 200 211. That is the spec number. And the release I am opening and showing it to you is release 17 H00. So this specification will contain all the details of the physical layer operations related to physical channels and modulation mechanisms. Of course, all the content that I have showed you in the PPTs has been extracted from here, everything. So I'll also pinpoint the material that we have studied, where you have to find that material exactly in this particular spec, so that if you wanted to add up on it and wanted to learn something more, so you can refer to these specifications and study it from here. Obviously, every specification in 3GPP would start with the scope and some reference documents, like what are the other documents that are in link with this. Or, for example, in the document, wherever they are referring to this other specification called as 38212, they will use this number 4. So the meaning of that is the corresponding connecting subject would be explained in this specification number 38212. Our internal linking is there to that. So it will contain a lot of definitions, symbols, and abbreviations of various kinds, like this. What is the meaning of different words? Now this spec starts with the numerology explaining what are the different numerologies that are supported. So you have the numerology starting from 0 to 6 and what is the subcarrier spacing for them and cyclic prefix related mechanisms. Then the frame structure, what is the least time that we have, and there is a TC defined, which is the smallest unit of time in 5GNR. All that I have introduced, this TC part and what is the timing and so on, related details here. What is the relationship between the TC in 5GNR and TS in 4G? This NTA offset I have explained to you at the time of timing adjustment related mechanisms. We learned that this TA offset is kind of common for everybody, timing advance related thing. TA is going to be separately sent for each individual subscriber. We learned that. Now, the number of slots and subframes, the number of slots per subframe, etc., for different subcarrier spacings. And the explanation will be about number of resource blocks we will have. So this is the flooring value of the number of K represents number of subcarriers divided by number of subcarriers in a resource block. Number of subcarriers in a resource block is typically 12. So divided, this is a divisional factor with the number of subcarriers. You will get the flooring value that will be converted into CRBs. Now there will be explanation about bandwidth part. We have seen that. So the corresponding details would be explained here. Now the modulation, this is the first topic that we have studied in our physical layer. So pi by 2 BPSK, BPSK and QPSK. So we have all studied this at physical layer. You can refer back here. So 16 QAM, 64 QAM and 256 QAM. How the bits would be converted into these modulation symbols. What are the different modulations we have? And up to release 17, we have 1024 QAM. That is applicable. This is the sequence generation is nothing but the pseudo-random sequence that I have introduced to you, nothing but the scrambling sequence. I have explained you scrambling sequence is generated from X1 sequence and X2 sequence. X1 sequence is constant, X2 sequence is kind of variable. X2 sequence initialization condition is variable based on the C init value. C init value is different for different channels. We have studied that part. But X1 sequence is constant, this modulo 2 operation. But this C init value will be separately calculated for each channel. For each channel, the condition is going to be different. I will show you exactly when we are studying each channel, what is the condition, where the condition is mentioned for the C init. But first 31 values will come from this C init computation for the X2 sequence. For X1 sequence, it's constant. We did not study these low PAPR sequence generations. We have kind of ignored them. That are not required. I did not include them in your curriculum. I did not explain them for you. Now, OFDM baseband signal, we studied this. We have seen this with example also. This is your symbol. So this is the same part I have explained you. This is your symbol. This is your IDFT operation that you are performing to convert it into number of samples. So delta F is your subcarrier spacing. The K value will be varying, which is going to be ranging from your lowest subcarrier number to the highest subcarrier number in your grid. So if based on the number of based on the size of the your grid and the number of subcarriers present in your resource block, you will be able to find out the K value, which is subcarrier number. So you will be changing the K value. K into delta F will be applying different subcarrier spacing for different symbols when you are converting them into IDFT samples. And this NUCPL typically represents your cyclic prefix length that will be added after the original symbols are generated once the symbol is converted into time domain samples. So all this part I have explained you. Now I'm showing you where that is located in your specification. Now the OFDM symbol for all the channels is the same, but for the PRACH, it will be little different. PRACH, we have delta FRA, which is lesser subcarrier spacing when you compare with the other channels. because we want the PRAT signal to be traveling for higher distance. So delta FRA would be different, which can be like, for example, 1.25 kilohertz or 5 kilohertz, 15 kilohertz, different possible configurations we have for delta FRA. So symbol again converted into IDFT samples. But how many samples, etc., how many subcarriers? I have explained you that there are different lengths are available, like 139, you have 839, different lengths are possible depending on the cell size and the distance. So you have to refer back that concepts to this particular thing, how we generate the PRH related signal. And again, you have to add the cyclic prefix part. Cyclic prefix is different for different PRACH configurations. We have learned that. So uh, the corresponding number of cyclic prefix elements will be added, components would be added. We studied that. Modulation and upconversion, I have explained. You take your SLPT, the signal that is generated, you convert it into, you multiplex it with your carrier frequency, which is F0. So this F0 is your carrier frequency. If you take, for example, if Reliance Jio case, it is like 3300 to 3400 or whatever. So megahertz. So that carrier mid frequency you take, and you take it as F0, and uh, depending on the SLPT that you have generated, so you're going to multiplex it with your carrier frequency to generate the, from the baseband signal, you generate the carrier wave and transmit into the air. Now, after these basic things are explained in this document, you will have, uh, you will have the channels divided into uplink and downlink. First uplink channels will be there, downlink channels will be there, then side link will be there. Side link channels will be present in your specification. Now, first uplink. Uplink is kind of divided into physical channels and physical signals. Physical channels are PUSH, PUCCH, and PRACH. Physical signals, all the DMRS and PTRS and sounding reference signals, the ones that we have studied. So some of them are called as channels, some of them are called as signals. Just a notation, just a convention. And now first the physical channels will be explained, then the physical signals. So first you will have uh, physical uplink shade channel. If you remember our physical layer process that we have studied all these operations, how the scrambling will take place, modulation, layer mapping, transform pre-coding, mapping to virtual resource blocks, and mapping onto physical resource block, all that we have studied. So all those things will be explained. For example, scrambling, placeholder bits would be scrambled like this. But if it is the data bits, the scrambling sequence would be used to scramble the BQ of I, which is your code word. So this is the same thing that I have explained to you while showing you this PUSCI channel. This is a scrambling process. So this is a CINIT value to compute your scrambling sequence. Uh, uh, for the second X2 equation, this is the CINIT value that you use for getting the first 31 values of the X2 sequence. You calculate it with by taking your present NRNTA value, and you take it with the RAP ID, and NID is nothing but your cell ID. You will be inputting all these details and computing this CINIT. But this CINIT is applicable only when you are transmitting message A in two-step random access procedure. In all other cases, you would be using just NRNTA and NID. RAP ID won't be there. Your random access preamble ID won't be there. But the preamble ID will become a factor when you are transmitting message A in two-step random access mechanism. We studied that. What is the modulation applicable? And what is the how the layer mapping is done based on the MIMO scenarios? We have studied that. Transform precoding, depending on transform precoding is enabled or disabled, you will be converting them onto DFT symbols. So you take your symbol, and so this is going to be your symbol, and you are going to convert it into DFT symbol. So this is the DFT operation. We learned that part. Those DFT converted symbols would be mapped onto your carriers, subcarriers. Then the precoding mechanism. Um, you take the pre-coding table, multiply it with the symbol vectors that are generated out after the transform pre-coding operation is completed, by dividing that with the pre-coding matrix, and you will generate the stream outputs. And there are different pre-coding matrix that are already listed. These are called as pre-coding code book. So TPMI indexes, these indexes are sent as part of your CSI, channel state information. TPMI index value would be sent, so, to indicate which pre-coding matrix we have to use. So for different antenna channel configurations, different TPMI values are applicable. So as you can see the tables over here, each different TPMI will result in different number of antenna outputs, depending on whether you are operating on 4x4, 4x2, or what kind of a configuration you are using for your antennas. Corresponding TPMI you take up and multiply your input symbol streams with the pre-coding matrix. I did not show you these TPMI tables in the PPT, but because I could not place them there because they're very big. So now you can actually see those things here. Next, uh, mapping of the virtual resources, physical resource blocks. We have studied that. So that is the explanation about physical uplink shared channel. But remember, uh, in your in this particular document, only in the physical layer, the bottom part of the spec will be present. Only the bottom part of the spec. What do I mean by the bottom part of the spec? I'll show you. So we studied this process. Now in this document, the 38211 that we are studying, you will be able to find out only this part, starting from scrambling onwards. So this spec kind of assumes that already the code word or code words are generated. It is the process starts for every channel. It will explain about the scrambling procedure, modulation mapping, layer mapping, pre-coding, resource element mapping, and OFDM signal generation. That's all. This part only would be there. This will be present in a different spec, which I'll introduce. The CRC attachment, channel coding, rate matching, code block concatenation, etc. So different specs will contain different pieces of information. Everything won't be placed at one location in the physical layer, especially. Now the same kind of explanations will go out for the other channels also. Physical uplink control channel, what kind of data would be carried, we studied. There are different PU CCH formats, and uh, you know, you are going to do different cyclic shifting or hopping, frequency hopping for different formats in different ways. That this part I did not explain you. This part I can kind of decided to ignore because it will be too much if you have to study for each format what is the frequency hopping mechanism that we implement. But for each format, what is the scrambling that is applicable, how the scrambling sequence, your X2 sequence will be initialized, and how the scrambling is done for each format. So for format 2, this is how it is done. And what is the modulation that we use, and what is the spreading and mapping into the physical resources. So that kind of will be explained for each different format differently. But again, we did not go format wise. I have only told you the general aspect for PUCCA channel. We did not study that entirely. But if you
Uh,
wanted to go in depth, this is where you can look for.
Probably one request, Banerjee. Probably format
Yeah.
0 and format 2, if possible, probably any of the time you can explain them. 0 and 2.
Okay, I will consider that request. If I can, if I have time, definitely I'll include that. Okay, format
Okay.
0, format 2, right? That is one you guys are using.
Probably long and short formats.
Okay, okay, fine. I'll try to include them.
Okay, thank you.
Then the physical random access channel, PRACH. Uh, so Pirach follows the Jadavcho symbols. We learned this Jadavcho symbol. So this is the Jadavcho symbol for which, on your constellation diagram, the angle, the theta would be, sorry, theta would be changing, but the distance R would be the same. So we learned that. So this is e to the power of j theta. So where R is the constant, we learned that section. So how the Jadavcho symbols would be generated. So the U value will be dependent on something called as it is uh, configured by RRC as part of system information, which U value you have to use. So there is a table for this U. We have studied that table. There is an index table. Based on the information that is provided in the SIB, you will look for that U, and from that U, you will be able to generate the Jadavcho sequence that is required for sending the preamble. But once the preamble is generated, the uh, but you have 64 different types of preambles. Each preamble is basically a cyclic shifted version of the previous preamble. How the cyclic shifting will take place based on this LRA, I have explained that part for you. For 64 different preambles, 64 different types of cyclic shifting we will take up. And of course, I also have explained you this cyclic shifting would also be dependent on the channel speed conditions. If the speed of the cell is very high, you will be doing the cyclic shifting in order to counter the Doppler effect of the radio samples, your signal samples. So cyclic shifting will be dynamically changing in case of Doppler effect or high speed cells. So based on that high speed cells, the configuration would be different. Based on the cell sizes, this LRA size, the number of symbols that we are generating also would be changing. How I have explained you how uh, different sizes will cater to different cell sizes. We have studied that part. So we ignored this Doppler effect related things. I have decided to ignore. I did not explain you these things. How the Doppler effect CV value would be computed. How what is the Doppler effect related parameters will work out. What is the shift and Doppler effect things. I decided to completely ignore. I told you the concept, but I did not go into it. But if you are anytime required of that, you can look here for that Doppler effect related things for how high speed cells the Prh transmission work out. So these are the different delta FREs depending on the preamble format that is configured. So you would choose the delta FRA based on the number suggested to you by the system information blocks. And what is the cyclic prefix size that you add for the number of samples that you generate after converting 839 frequency domain symbols into 24,576 time domain samples when you are transmitting on the channel. I have explained all this part. So the reference is here. And these are the different other formats, A1 to C2 format, which are using 139 size. And what is the uh, possible configurations? I explained all these parts while we are going through PRATCH, but we are just studying it here. So this is the logical root sequence number, the U value. You get the I value from the SIB, you have to get the U value from here, from this table. This table is different for different sizes. For LRA 839, this table is applicable. For LRA 139, this table is applicable. For LRA other sizes 11,000, 1151, this size is applicable. And for LRA 571, this table is applicable from where you will be getting this root sequence number that is used for generating your PRATCH. Now this zero correlation zone configuration is nothing but Doppler effect configuration. Unrestricted sets are used for low speed cells. Restricted sets are used for high speed cells. And there is a zero correlation zone configuration value that will tell you what NCS value you have to apply. This NCS will kind of tell you what is the amount of Doppler effect in the cell. This will be determined by the operators by performing the drive test in the cell. So they will configure it accordingly. Okay. Now we go to the physical signals. We learned about reference signals. Reference signals are known signals which are generated from the scrambling sequence. C of C of 2n represents the scrambling sequence. So uh, you take the scrambling bit either 0 or 1, and if you substitute here, what you will get is plus or minus 1 by square root of 2 plus or minus 1 by square root of 2 j, which is nothing but QPSK symbols we have studied. So all reference signals are QPSK symbols only, but different types of reference signals will be generated by using a different scrambling sequence input. So C unit is going to be different. For example, for a PUSCH demodulation reference signals which are traveling along with PUSCH channel. So the C unit value would be computed from here, and the C unit value that is used to initialize the first 31 values of X2, from that you calculate the scrambling sequence. The scrambling sequence bit would go here, and we will be able to come up with this R of n, the PUSCH symbols, PUSCH demodulation symbols that you have to transmit along with PUSCH to help decoding the PUSCH channel. Zero correlation zone is basically a technical word to actually correlation means kind of orthogonality, we call it. I did not actually go in that depth, correlation is orthogonality. If two preambles are transmitted, they must be orthogonal. Normally, if two idle mode mobile phones, when they are sitting in two different positions and transmit the preamble, typically both of them are orthogonal, definitely, because of the Jadov-Chow property. But when they are moving at that too at a very high speed, typically what will happen is that correlation won't work out. Sometimes your genome won't be able to detect what is the preamble that is transmitted because of the Doppler effect and the speed of the mobiles traveling. So to counter that, do we have to achieve zero correlation? Meaning is you have to achieve full orthogonality. You have to make sure that there is no there is no preamble uh, changes that are leading to failure in detecting the preambles. Corresponding settings, they have used this technical word called a zero correlation zone configuration to achieve that orthogonality. That correlation is conflict basically, or avoiding the conflict by solving the Doppler effect problem. So that is a technical word. We should not dig much deep into it. Why they have used that word? It is related to Doppler part. Rohan, we'll ignore
Okay,
that. Okay. Yeah. Okay, so uh, demodulation reference signals. So for every channel, how the demodulation reference signals would be generated. So a phase tracking reference signal, even phase tracking reference signal is a modified version of demodulation reference signals itself. I explained you that. And demodulation reference signals for PUCCH, which uses a different CRNTI, so different C unit value. So for every channel, you will have different C unit value while generating your reference signals. I have explained all of these things while introducing those channels. So here is where you have to look for if you are digging for more details. Sounding reference signal, the last one. So even the sounding reference signal is an modified version of your reference signals itself, basically cyclic shifted version of it. And what are the different thetas that are applicable for the sounding reference signal? This alpha I kind of gives you the theta value or angle in angular modulation symbols. But I did not go to that level. We have ignored it. I have only explained you higher level information related to sounding reference signal. Okay. So that covers uplink channels. Now we have the downlink channels in 38 to 11. Again divided into two categories, physical channels and physical signals. First, they will explain about the physical channels. The story is the same. It is kind of a repetition. I won't waste much time, but it is kind of a repetition. So you have how the scrambling would be done. What is the C unit value for computing the scrambling sequence for PDSCH channel? What is the different modulations that are applicable for PDSCH? how the layer mapping is done. Of course, transform precoding is not there for downlink. Directly, we do the antenna port mapping and virtual resource blocks and resource blocks finally. Similarly, for PDCCA channel. So I have explained you this concept of CCE, core sets, um, REG bundles, REGs, resource element groups, etc., etc. So all this part is covered in your as part of your material. This is there. We have studied all this detailing, the core sets and CCE related things. How the scrambling is done, what is the scrambling code generated, and what is the modulation that is applicable for PDCCH, QPSK, how the data bits are converted into symbols, which physical resources we use. Similarly, PBCH channel is part of your SSB block, how the scrambling is done, and modulation mapping onto physical resources. It is part of SSB. Which resources are applicable for PBCH? We have already studied that as part of SSB. Physical signals, you have all the reference signals, the same story. Every reference signal would be calculated based on a separate C unit value by using that channel related parameters, like which symbol we are using in which slot, and this n factor lambda SCID provided in the as part of RRC configuration. Lambda value also is provided as part of RRC configuration. From that, you will be able to compute uh, what demodulation reference signal you are receiving in which symbol position of a slot. Once you have seen it, you can calculate scrambling sequence. From that, you can calculate reference signals. So same thing repeated for all the other reference signals as well. Now, we have synchronization signals, primary synchronization and secondary synchronization generated with the special sequence. We have seen the simulations also for this PSS and SSS. So 1 minus 2 x of m. X of m is computed from this equation with these initial values. We have studied how that works. We have studied the PSS that comes from here. It is the size 128. It will occupy 128 symbol positions, PSS. SSS occupy also 128 symbol positions. And the SSS calculating formula is different. Here we use two sequences, X0 sequence, X1 sequence. We have studied what is their significance, and they are initiated differently and everything. From this, mobile would be able to compute something called as NID1. Mobile would get NID2 from the primary synchronization signal that is used as one of the input while generating the sequence. From this NID2 and NID1, mobile would be able to compute the NID, nothing but the PCI, cell scrambling code. Now, SS and PBCH block, we studied this detailedly in the physical layer, how this whole operation works out. I don't go much deeper into it. I explained you all this. So we have studied like which in the SS PBCH block, which positions would be occupied by PSS, which positions would be occupied by SSS, PBCH, or PBCH DMRS symbols. We have looked into it. It will be dependent on V. V will be dependent on the N cell ID or the scrambling code that is calculated from PSS, SSS. We have studied that. Okay. Side link we have ignored. So we did not study the side link part. Side link is like V2X, etc., mobile to mobile communication. So that is not part of our curriculum. So we did not go there. So that's it. So this 38211 physical layer spec gives us this entire, uh, you know, lower layer part of, or we can say code word processing. It will contain the code word processing for all the channels. Okay. Next one. I will little go fast. I have to introduce all the specs. Okay. This is 38,212, 38.212. Uh, this contains only multiplexing and channel coding related operations. So this is going to contain the first half of the physical layer that we have studied. So this part it will contain. So how the CRC would be attached, code block segmentation would happen, CRC attachment for each code block, how the coding would be done, rate matching and concatenating all the code blocks to generate the code word. So this part of it for every channel. So uh, again divided into three parts: uplink, downlink, and side link. Uplink, you will have uplink SCH, RACH. These are what we call as transport blocks. So the transport blocks would be processed into physical channels, physical channel data. Uplink SCH would be converted into PUSCH. RACH would be converted into PRACH signal, which is a special preamble signal. If it is control information, UCI, uplink control information, it either would be sent on PUCCH or PUSCH placeholder bits, would be sent in two different places, on two different channels. Downlink, downlink SCH transport block is carried on PDSCH, BCH transport block is carried on PBCH, PCH transport block is carried on PDSCH. Control information goes on PDCCH. Side link we are ignoring. Now, this will contain the mathematical mechanisms behind your CRC calculations and all the process, which we did not go through. If 24-bit CRC need to be calculated, how it would be found out, how that 24-bit CRC would be calculated. If it is 16-bit CRC, 11-bit CRC, 6-bit CRC, there are different versions of CRCs. So the mathematical mechanism behind it. Now, how do we do the segmentation, code block segmentation? I've told you if your code block size is really big, there are some particular sizes that are allowed. If the code word, if transport block size is bigger than this, it will be divided into segments. For different coding mechanisms, the size will be different. For example, LDPC coding, we have the upper layer size to transport block size to be 8,448 bits or 3,840 bits, the code block sizes. This is for polar coding. The 1706 is 1706 is applicable for polar coding. So depending on what kind of coding that we are going to use for that particular channel, these sizes would be varying. We studied this part. Now the actual channel coding, polar coding, how the polar coding mathematical algorithm work out, etc. So the mathematical process behind it. Low density parity check coding. What is the mathematical process for that? But a lot of these mathematical processes I have ignored. We have only studied few. But detailed information is here, how it happens. This channel coding of small block lengths I have explained to you as part of PUCCH part, how the channel coding works out for small blocks. That is here. Rate matching is to match your code word to fit into your resources. I told you that. How do you do interleaving? Juggle the data is what we call as interleaving. Blocks would be interleaved, bits would be interleaved, and we do something called as puncturing. All that will take place here. You do the bit selection or bit pruning as part of this to perfectly fit our code word into your physical resources. So corresponding mathematical process. Finally, all the blocks that are subdivided will be concatenated. We'll be adding them by running it through a uh, for loop or while loop. In a loop, we will be adding each one together to form the code word. And that code word is going to be sent to 38.211 document once the code word is formed. So 38.211 explains what happens to that code word. 38.212 explains how this code word is generated by individually, performing all these activities. And now I told you these activities are going to be different for different channels. You see the note here. All these step procedures are not equal to all the channels. They are different. So now this document first explains the common procedures, and then they will take up each channel one by one. For random access channel, what will happen? Random access channel just is a preamble number. There is nothing that will happen actually at the physical layer level. There is no channel coding all that required for random access channel. But for all other channels, how do you do the CRC calculation? uh, what is the coding technique we use, LDPC coding or segmentation or CRC blocks, etc. What is the rate matching mechanism? So for every channel separately, what is that applicable for that particular channel? So if you are carrying the uplink control information on PUCCH, how it will be processed? If you are carrying it on PUSCH, how it will be processed? It will be separately processed. Are two different techniques we follow. And that too, we have different types of uplink control information. For each type, the processing is different. Uh, uh, well, they are going through this mechanism. So the corresponding explanations. Similarly, downlink, once uplink channels are completed. PBCH payload, I told you PBCH will include the timing related information, your radio frame number and what is the uh, other timing related details like SS block number, etc. Those details will be appended to in the PBCH additionally on top of whatever the data that we are getting from the higher layer. So what kind of bits will be appended? I have explained you all those bits in the table. So you have the table present in the material that is sent to you as well. So that PBCH related details. So most significant bits of the block index, SSPBCH block index will be added here. We studied that. So individually, how the scrambling would be done, uh, transport block CRC attachment would take place, channel coding will happen, and so on and so forth. So for all the channels, rate matching and converting it into a code word. So for every channel, the same procedures. How the CRC would be added, what kind of coding, how do we do the rate matching, and how do we concatenate to form your code word. Same thing for DCI as well. And here starts side link channels, which we'll kind of ignore. So these two documents together will explain the complete process of the physical channels or physical layer operations, this entire thing. There are other two physical layer documents also that are in place, which I'll introduce them later. Otherwise, I will show them now itself. Okay, so this is also physical layer spec 38 to 213, 213. Again, the release number is release 17. This document contains physical layer procedures for control operations. If you remember, we have learned that uh, every protocol layer will have its own control mechanism, every protocol layer. And as we are studying all the protocol layers, we learned about this control mechanism that is applicable. So at physical layer level also, we have this control mechanism, and how the physical layer control mechanism works out. That is explained in a separate spec. But when you take it to MAC, RLC, PDCP, and SDAP, their control is included into their documents itself. They are kind of not present separately. The control mechanisms that is involved in every protocol layer. But for physical layer, it is present in this separate spec 38, 2 and 3. So what will be done here? So how the cell setch will take place? So for a different subcarrier spacing, how the cell setching will work? So general procedures related to the mobile, how mobile will adjust to the transmission timing when it is first time accessing the channels, like the deeper details of the physical layer aspects. If you are activating the secondary cell, how you will adjust the primary cell and secondary cell timing related offsets. So that mechanism. And we have studied about this power control, uplink power control, by using some special RNTIs, power control RNTIs, uh, TPC RNTIs, transmit power control RNTIs. Will control the power of uplink shared channel and uplink control channel. Will uh, cover. So it will be listening to PDCCA channel to find out the corresponding power control commands and apply that power control. We studied that part. The corresponding explanation will be present here. But for random access channel, we start with the initial power, and after that we will be incrementing the power every single time. Once we start with the initial power, we learned that. Uh, we call that as a power ramp up step. Uh, that we have studied in PRACH. So how that power increment will work out, the corresponding details would be explained here. dBm is decibel milliwatts. The corresponding mechanism is explained. Now, power headroom report. I've explained you this power headroom report. Each power headroom value corresponds to what, uh, index values will correspond to what power values. Those kind of explanations will be available here in this particular place. So I will show you that. Okay, they did not put it in the form of table. They have put it in the form of an equation. So this, based on the power report, the power headroom report that the mobile sent, if you substitute that value, you get some information, which is actually used in the scheduling mechanism also, these power headroom reports. We have studied uh, this power headroom related things at MAC level in the form of MAC control element. But how that power headroom works, the corresponding information is explained in this document 38213. So sometimes there will be linking between MAC layer and physical layer as well. Actual report is sent by the mobile equipment's MAC layer, because this power headroom report is used for scheduling, uplink scheduling. Um, but power headroom measurement is dependent on the physical layer, which is a physical layer operation, because power is nothing but a physical layer operation. How to transmit, how much power you are transmitting in uplink, what is your power class, and a lot of other factors will be involved here while calculating this power headroom value and reporting it. So the corresponding explanation is present in the physical layer. So MAC and physical layer have to kind of coordinate here. MAC completely will be dependent on the physical layer information for sending this power headroom report, MAC control element. Now, random access procedure, we have studied that very detailedly, random access procedure, uh, random access preamble, and there are two types of random access procedures. We studied both, type 2 random access procedure, type 1 random access procedure, two-step and four-step random access procedures. We learned that. And what are the uplink grants that are used, and contention resolution identity, the CRI that you will receive. I have explained all these things step-by-step process. The corresponding explanation will be available here. Actually, when mobile equipments are being developed in the companies, they will actually go through these specifications and develop the procedure or related software on the basis of the explanation provided here. What I did, I read this information and converted that into a PPT and presented it to you. That's the kind of difference here. So all these are rules. Now, when you are reporting HARC Act NACs, what are the rules? And when you are reporting UCI, what are the rules? And in which resource sets you are going to transmit the UCI? We studied. Um, so here the complete detailed explanation will be there related to it. So all control channels related information will be explained in this document. Uh, HARC ACNAC is part of physical layer control information, ACNACs. UCI or DCI, both are your control information, downlink control information and uplink control information. It's all be part of control. Okay. So this is 38,213. We have 38,214. I will introduce that later while we are studying the handover related mechanisms because there is a linking to it. I will introduce that. Now the next spec. Uh, that is the three important physical layer specs which I have introduced so far. Now the next one is the MAC, which is medium access control 38.321 release 17. Most of the layer 2 specs, they will kind of contain divided it kind of provides information related to services. What are the different services MAC layer will expect from the physical layer? Because always higher layers will expect the services from the lower layers. So what services MAC will expect from physical layer? So it wants physical layer to transfer its data. It wants physical layer to provide its ARC information or send the scheduling request, SR, a 1-bit scheduling request that we transmit on the PUCCH channel. Or you require channel quality indications as part of your scheduling mechanism for your scheduling operations. So MAC kind of demanding the physical layer to provide all these details. It says that I need your support for doing my duties. This is the kind of support physical layer must provide to MAC layer. Similarly, this will also contain what services MAC layer will provide to higher layers. So MAC layer will take the data of the higher layer and send it across by converting it into a transport block and processed to the physical channels. It would be sent across. And there is radio resource allocation mechanism that is present here. So that is the scheduling part which we have studied. Next, the channel structures. What are the different transport channels mapped onto what are the different logical channels mapped onto which transport channels? We have seen that completely. Of course, we have ignored the multicasting channels and side link channels. So only we have considered these primary channels: BCCH, PCCH, CCCH, DCCH, and DTCH. Now, MAC also will play a very important role in random access procedure, and we have studied that how the random access preamble index will work out, and it is a complete random access procedure in detail we have studied. So complete random access procedure related explanation, what kind of role MAC will have to play, when it will have to send two-step RA, four-step RA. I have showed you algorithm also for that. When we will be sending two-step, when we will be sending four-step, how it will be transiting from four-step to two-step, etc. The complete thing. So this entire 5.1 section is about that. It will completely explain about the random access mechanism and how it works. So whatever the information that I have presented to you is taken from here itself. Is taken from here and converted into presentable for points and showed to you. But if you have to find out the information on the original source, you will get it here. Now in these MAC specifications, the most important thing that you have to look for is these slanted words. Whenever you see a slanted word, italics, you see, you have to understand that that italic is basically a parameter that is configured by higher layer. Typically, that higher layer represents RRC. So RRC provides you this information as part of either system information or provides you as part of RRC parameters when they are sent to you. For example, the preamble that you have to use, if you are using contention-based random access procedure, the preamble you have to use is provided to you by the system information. You have to use a general preamble. But if you are using a non-contention based random access procedure, you have to use the preamble that is sent to you either in the PDCCH order or it is given to you by RRC information. We have studied different types of random access mechanisms in MAC layer. So special preamble would be sent to you, non-contention based or contention free random access preamble uh, by the network. So, but that is done at a dedicated information level at RRC. So this parameter either would be coming in the form of SIB or either would be coming in the form of RRC dedicated details, RRC dedicated information. But it is kind of giving you a hint that You have to look for these details in the higher layer specifications or RRC. So everywhere that slanted words are seen, definitely you have to link them up to the higher layer. That is how you have to study the specifications. This is true whenever whenever I'm talking about all the layer 2 protocols, uh, MAC, RLC, PDCP, and SDAP. Every case, this is applicable. If any configurable parameters are there by RRC, this is how they would be presented in the spec. So basically, the configuration is coming from the RRC. So there are a lot of configurable parameters for random access procedure, and they would be coming in from in various positions, like PRACH configuration frame offset, message PRACH configuration index, uh, two different sizes we have, and the message is used in two-step random access mechanism. What is the initial power that you start transmitting your preamble? And how many times you can transmit two-step random access procedure, maximum number of times. Like each and everything that we have used in our random access procedure as conditional parameters, they're all coming in from RRC. So the parameter, the corresponding explanation, what is that parameter is, for example, power ramp up step, the power ramp up factor every time, how much you have to increment when your preamble is not responded back with from the network. Because you are starting with the initial power at the starting. So that value, like that. All these things will go into the mathematical algorithms in deciding the next steps while you are performing any procedure. RA occasion list, when you will receive your when you can transmit your RAs, how many times you can transmit RA in one time domain location, and frequency domain, how many times you can transmit that part. Okay. There are two types of message types, Group A, Group B. If message 3 size is bigger than Group A, you have to use Group B preambles. If message A size is smaller than Group A, you have to use Group A preamble. So that Group A, Group B related configuration. Again, Group B configuration for 4-step random access procedure, Group B configuration for 2-step random access procedure. This is depending on the message 3 size. How much time you will wait for your random access response, RA response window? How much time you wait for contention resolution identity to come in the downlink direction? How much time you wait for message 3 in case of 2-step random access procedure, etc. So the whole process will be explained in some kind of an algorithm kind of manner. Okay, what is this one greater than symbol? What does it represent? So this is something you have to understand about the specs, 3GPP specs. Whenever you have uh, one and this greater than symbol, that is kind of at first level point. Now, when you see a 2 and greater than symbol, this is a sub point inside this first point. So we are going inside of this first point. That is the meaning of this. So when you are reading the specs, you have to kind of consider that. Sometimes you will have 3 greater than, 4 greater than, 5 greater than also. That means we are going into sub steps. It is like that. So basically, this is a sub step of the step itself. But these steps did not have the sub steps, direct steps there. So step by step, it is explaining the process, step and sub steps. This this whole thing, I have actually these steps and sub steps, whatever that are presented here, I have kind of converted that into an you know uh, when it was presented to you, it was kind of converted into an message sequence chart and presented to you. I'll show you that once. I'll show you that and tell you how you have to basically relate the things. So we studied this, the random access procedure, message sequence chart, when the two-step RA, when four-step RA will be applicable. Now, how did I come up with this particular, this picture? Where I got this? So this is basically a conversion uh, tactic of the information that I found out here in this particular explanation, step-by-step process. So exactly when we are going to do what thing. So kind of we have to study this whole thing. If you convert it into in a shortcut thing, it will become the message sequence chart. So when you have to read it, you have to understand these if and else's conditions. If if so there when that condition is true, it will suggest something to do. Else, what else you have to do? So there is a else part explained. So if this is not applicable, then else if there is any other condition, then what you have to do. So that is how you have to understand these specs when you are going through and reading through. So they kind of put it in the form of programming kind of stuff, like if and else things will be present. So you can easily understand them when you are reading through. Okay. The next thing is downlink SCH data transfer. Now, how the downlink assignments will happen on what RNTIs, you have to listen to PDCCH channel, find out how the exact ARC operation should happen. We studied, but again, the complete explanation will be available for you in the text format, in step-by-step fashion, steps, sub-steps, sub-sub-steps. So based on those rules and conditions, your algorithm should work. So whatever the kind of software that you develop should be following these rules that are put here, the conditions that are put here. Same thing for uplink SCH as well. But while sending uplink SCH, you have to have additional procedures also like scheduling request, buffer status reporting, how when you send buffer status report, periodically you can send buffer status report, and how the logical channels are grouped. Uh, Again, all this configuration is provided to you by RRC, these slanted things, italics telling you that. And for power headroom report also can be sent periodically or event driven basis. Like when your power value suddenly drops down, uh, suddenly you lose 2 dB of power, you can send power headroom report. Uh, by you basically you're reporting the network that you're experiencing some sudden power drop. So that two types. So corresponding configuration. So if it is periodic, what is the periodic PHR timer? And after sending a PHR once, how much time you are not allowed to transmit PHR? This is the one I am talking about. The PHR TX power factor change. Suddenly your power dropped down for some units of time, some power units, dBs. You have to send a power headroom report. What is the value that is applicable in this particular cell? RRC configures that. So based on it, mobile would be sending this power headroom reported control element. Preemptive buffer status, we have ignored it. It is applicable only for IAB cases. So we did not study that. Timing advance reporting. There is timing advance uh, command that must be coming to the mobile every now and then. So there is a timer associated with it, etc. So these parameters are configured by the higher layer. Okay. So various operations that MAC layer does will be explained in Here in this document, how the PCH reception will be processed, BCH reception would be processed, how the discontinuous reception works out, DRX, the DRX mechanism we have studied. So the DRX mechanism, I have kind of, so these are all the parameters that are in place. So I kind of converted that uh, into this. So when I have explained it, sorry. So all these parameters and how do you control this DRX mechanism? We have seen that part. So here, so this whole working mechanism of DRX would come from here, would come from this explanation. Okay. So likewise for every different thing. So depending on what area that you are looking in, you have to go for that particular section and study that particular subsection. And each and every individual Mac control elements would be explained here. What is that control element will do, and when you have to transmit the rules and regulations related to it. There are a lot of control elements. We have seen some, we have ignored some. Now, at the end of the spec, after these procedures are completed, individual procedures are completed, you will have the protocol data units, how to construct the MAC PDU, what is the different header mechanisms that are applicable, the LCID, CLCID, ELCID being 2 bytes, 1 byte, what is the LCID value that you have to use for it, and so on. So this whole design mechanism, designing of the um, designing of MAC protocol packets, MAC PDUs or MAC transport blocks. So I have studied this with examples and different MAC control elements and their designs individually. For example, if it is BSR, it will contain logical channel group ID and buffer size. If it is short or truncated BSR. If it is long BSR, you will have only buffer sizes. Maximum 8 groups you can report for long BSR, that design. So all this part we have studied. So you have to look in this particular position when you are when you wanted to find the information about the MAC layer. So the complete MAC layer parameters and so on would be present here. What is the message B design? We studied this also, message A design, message B design, and so on. Uh, Timing advance command, uplink grant, and temporary CRNTI. And we have studied various examples with it as well in the MAC layer, that part. 38.321, the MAC layer specification. Next. 38.322, RNC specification, radio link control. As I told you, almost all the protocol layers will contain this mechanism. What services this layer will provide to upper layers. So RLC offers 3 types of data transmission services, TM, UM, and AM. MAC layer offers um, RLC kind of expects this from the lower layers, which is nothing but the MAC layer. It expects the lower layer to do the data transfer. Now here, remember the important linking point. If RLC is expecting MAC to do the job and do the data transfer, it is not done by MAC layer independently or individually on its own. MAC, of course, will be taking the help of the physical layer. That linking will be available in the MAC protocol specification. But RLC won't consider physical layer into its consideration. RLC but don't know there is a physical layer. RLC simply will be dealing with the MAC layer for everything. It is dependent on the MAC. So it kind of tells the MAC layer that there is so and so much amount of data waiting in my buffer, take it and send it. How MAC sends it, What kind of services Mac use from physical layer? RLC don't care about it, don't bother about it. From RLC point of view, Mac is its lower layer from which it is expecting some services. Okay. Procedures. How the RLC entity must be established and what it should do. At the re-establishments, it should stop all the timers and reset all the variable values and your sequence numbers, everything it will be reset. It will discard any of the SDUs that are received from the higher layer at the time of re-establishment. We have kind of linked this to PDCP layer. If you remember, we have studied something called as PDCP level status report. When PDCP is sending the status report in case of handover situations, RLC will go for reset because of the re-establishment of that. So we have linked it up there. So that corresponding explanation is present here. What RLC is supposed to do when it is asked by the higher layer to get released, and how it transfers the data in different modes. In TM mode, what it should do. So the complete these things I have explained you with these are state variables. We have studied window sizes and state variables. So with the help of if and else, these conditional things, kind of step by step procedures will be explained here. What is the next when you have to perform the next reassembly and so on. All these are state variables. We have looked into this. So it is the actions for each mode, uh, UM mode, AM mode, and so on. What should be the next sequence number? On what basis it will be decided? It is called as TX next. How it will be incremented, and when you will be requesting for status report, and so on. Completely status report related things, ARQ procedures. When how the retransmission will happen? When do you send status report? Corresponding explanations. Polling, whenever polling bit is set to 1, you are requesting for status report. How that works? What are the rules for it? We have studied poll byte, poll PDUs, and their explanations. SDU discard. If PDCP is requesting you to discard the packet in case of PDCP level discard timer is expired, even if it is submitted to RLC, RLC need to discard it. So not only PDCP will discard the things, PDCP can come and tell RLC also discard a packet. That if it is waiting in our buffer for more than discard wait time, discard timer value. So from any of the two buffers, it can be discarded from either from PDCP buffer or RLC buffer. So that part. Data volume calculation while reporting the data volumes to the MAC layer. Because on the basis of it only, MAC will be preparing buffer status report based on this data volume calculation. And then it starts the protocol data units. Uh, each RLC PDU designs what headers we will have. In TMD mode, there is no header. In UMD mode, you have this, only containing the SI reserved bits. So what is the different designs? We have studied all these things with examples. SI sequence number and higher layer data. Sequence number will be there only in case when the data is getting segmented. We studied that. Otherwise, they are filled with reserved bits. In case of UM mode, we use it only for ordering. Um, Only for reassembly, we use the sequence number in UM mode, not for ordering. Sorry, only for reassembly. So sequence number, different sizes that are allowed based on the RRC configuration. Then AMD mode. In AMD mode, you have device bit because data is there, control is there, polling bit, your segmentation information, sequence numbers can be of different sizes. And there is a segmentation offset if the data is getting segmented. Status PDU, which contains E1, E2, E3, we have studied that. What is E1, what is E2, what is E3, we studied different examples for that. So that whole part is here. And all these parameters kind of will be explained in a detailed fashion in this particular section for 6.2.3. Each and every parameter, what are the different possible sizes, what is the meaning of that particular parameter field means, it will explain. Zero means, for example, in case of device, zero is control PDU, one means data PDU. Polling bit P, zero means status report is not requested, one means status report is requested. We have studied all this. That's it. That is going to be the end of the document that will lead you. Again, if you observe here, again we see this slanting italics here. So these are the timers that are configured by RRC. So the configuration details must come from RRC. T pole retransmit, T reassembly, T status probe bit, or what is the maximum retransmission threshold in case of RRC, AMRRC, AMRLC, polling PDU or pole byte value. So these things would arrive from RRC protocol. Higher layers, we call it as. Timers that are configurable, uh, some parameters that are configurable by RRC. That is 38.322 RLC spec. Two more specs, we'll see them and continue. 38.323 is the PDCP specification. As usual, it starts with PDCP structure, architecture, like PDCP works only for RLC, UM and AM mode entities. What are the services PDCP provides to the upper layer? Like if upper layer data is given to PDCP, PDCP kind of ciphers the data, compresses the data. Three types of compression, we have studied that. Uplink data compression, header compression, and we also have studied Ethernet header compression. In this header compression itself, we have both those things, ROHC compression and Ethernet header compression. But uplink data compression, which is newly added in release 17. Ciphering and integrity protection, that is done by the PDCP. And what are the services PDCP expects from the lower layer? From PDCP point of view, again, the lower layer is RLC. So it is kind of expecting the services from RLC. Two types of data transfers it is expecting from RLC, either acknowledged data transfer, unacknowledged. Meaning, in unacknowledged mode, RLC need to take the data from PDCP, doesn't need to send any acknowledgement to PDCP protocol, even after it is successfully transmitted. Anyway, UM mode never know whether it is successfully transmitted or not. But AM mode entity, with the help of the status report, it will get to know whether the RLC SDU is successfully transmitted or not. Once RLC gets that report, RLC need to report it to the PDCP because PDCP is expecting that. So that is the kind of data service PDCP is expecting from RLC. PDCP won't work for TM mode, only work in with RLC operating in either AM or UM. What are the different functions? All the things that we have studied, like header compression, decompression, ciphering, deciphering, integrity protection and validation, SDU discard on the basis of timers, and so on. Out of order delivery, reordering, and duplicate discarding. I have showed you some cases for duplicate discarding as well, when the duplicates will occur and why we have to discard them. We have seen some call flows related to it at PDCP. So how the PDCP entity would be handled? What are the rules and regulations that are applicable for PDCP? How it will transmit the data? What are the rules applicable for while transmitting? What are the rules applicable while receiving? When you have to send the status report related rules. Anyway, we have seen call flows related to the status report. So the corresponding explanation will be available here. Status report. If you send the status report, um, when you have to send the status report, when you receive the status report, what you have to do? Data volume calculation is same. Just like how RLC computes the data and report to MAC layer, PDCP also computes its data size pending in the buffer, which for the data that is not yet processed and sent to lower layers, and it will report to the MAC layer. This how the ROHC compression algorithm works. We have studied this ROHC algorithm, three states, and the explanation related to that. We understood that whole process. So the complete ROHC related mechanism, how it work, how the context will be created, and how many contexts can be created, and so on. How the compression mechanism works and how the decompression works, and related operations. Ciphering. In ciphering, by using these values, for example, this by using um, this count to sorry count value, direction, bearer ID, key, etc. You will be ciphering the data. We studied that part. So you will be using different keys for RRC, different key for user layer, and they would be coming in from the higher layers. These keys, which is how the keys will be computed. We study in the NAS protocol. We'll understand that. But by using it, your data can be encrypted, and on the receiving side, it could be decrypted. Same way, integrity protection. Uh, Integrity protection also will use similar details, like you have the bearer ID, you have the count value, direction, and the key that is used for calculating the MAC-I. You calculate the MAC-I and send. With the help of it, you can validate the integrity mechanism of integrity of the message. PDCP duplication we have ignored because we did not study dual NR cases. That is not part of the curriculum. We have ignored that part. Please don't confuse with duplicate discarding. Duplicate discarding is different. PDCP duplication is different. When dual cell cases are involved, PDCP would duplicate the PDCP data and send it on two different RLCs, which goes to two different cells. The explanation is related to that. When you require it, you have to study the concepts that are present here. Ethernet header compression, we have introduced it, but we have kind of ignored. We did not study much details related to the Ethernet header compression as it is related to private 5G networks. But I showed you higher level things like what is the MAC header that will be compressed and so on. So it can kind of work along with ROHC or it can work independently. We have seen that. So two different configurations possible. Only EHC compression or EHC plus ROHC compression. Two different mechanisms. Uplink data compression. This also we have studied. Okay. Now the PDCP data units and the protocol parameters. Uh, so different formats. What is the header that we attach? Just PDCP sequence number MAC-I for SRBs. Our PDCP sequence number size can be like varying. MAC-I kind of optional in some cases. When it is optional, it won't be present. But this is 12-bit sequence number PDCP size. This is 18-bit PDCP sequence number size. But other than that, which one you should use? RRC configures. RRC tells you. So this is RRC configurable parameter. Side link we did not study. And different parameters that are applicable. Like feedback packets, we have studied all the feedback packets, ROHC feedback packet, Ethernet header feedback, and UDC data feedback, and each parameter explanation. MAC-I how many bits, count how many bits, reserved bits, D by C represents what are the different PDU types we have. 0 represents PDCP status report, and these numbers represents feedback, and so on. So the complete explanation about each and every field once again. At the end of the document, again, we have State variables that are used in live by the PDCP specification or PDCP software, live parameters are called as state variables. Those are not configurable. PDCP itself will decide. Like for example, what is the sequence number you have to use for the next PDCP packet is called as TX next. That is decided by the PDCP layer only. It is a basically incremental circular value, goes from zero all the way up to maximum size and come back to zero. But for every PDCP SDU, it will be incrementing once. So it is locally maintained, not required to be configured. Its size will be configured by RRC, but its value won't be configured by RRC. Value is decided by PDCP. That's what we call it as state variable. There is a constant which is the window size, and there is a timers, discard timer, t underscore reordering timer applicable for PDCP, configured by RRC again. And that's the end of the PDCP spec. And some additional details are put here, added, which is fine. Some examples have been added, different UDC related examples and so on. Yeah, EHC related examples. I have put actually EHC related things in your material, this part, but we did not study them because not part of our curriculum. We've ignored it. Ethernet header compression. Okay, one last spec I'll have to introduce. That spec introduction would be done. We can move on to the next subject. Sdap. We studied Sdap. So Sdap structure, it works with multiple PDCP entities when it is sharing, when one QoS flow is mapped onto multiple radio bearers. So yesterday, when we have studied the entire QoS flow mechanism, we introduced this concept. So how the Sdap entity gets, what kind of services Sdap provides to higher layers? It takes the higher layer data, user plane data, and transports it. But it will be kind of expecting a lower layer to do the data transfer, same thing that it is giving, providing to the higher layer. It expects the same thing from the lower layer. When does the Sdap entity gets established, and when it will be released, and so on. I have already explained you all these things. When a QoS flow is coming up, if Sdap is not yet configured, you have to configure Sdap. Otherwise, it's already configured. It will be there only one time for one PDU session. All those rules and regulations we studied yesterday. How many Sdaps would be there and so on. That related rules here. Data transfer. What does it do? How it transfers the data in uplink, downlink? Explained everything. For example, in downlink, we have studied if you receive the reflected quality of service RQI bit set in the Sdap information, what need to be done? You need to report it to upper layer, which normally nothing but your NAS layer. You will be reporting it. RQI related data. So for uplink, again, what is that you have to perform? So this RQI handling we have studied, inform it to the NAS layer. The QFI RQA handling, reflective quality of service handling. And what are the protocol data units that are present in this SDAP? Very minimal headers. Without SDAP entity configured with header, you send the data as it is to the lower layer when it is one-to-one mapping. But when you have the QFI configured, in case of downlink, you get this RDI, RQI indication, and actual RQI notification whether it need to be sent to NAS layer or not. The QFI, QoS flow identifier, detecting this data belongs to which QoS flow. In uplink, you have only the QFI. RQI bits won't be there. RQI will only happen in downlink, but it is applicable for uplink. But you have the D by C and R. D by C is required because we have the data as well as control applicable for SDAP. In the control, you kind of will be able to send something called as the end marker when you are stopping the data transmission on a particular QFI. When your quality of service flow is getting discarded or being stopped, we'll use this end marker to report it to the gnode B that I'm stopping the data transmission on this DRB for this particular QoS flow. I'm using a new DRB for that sake. So these are the minimal headers that we have in the SDAP part. And we already linked SDAP with PDU user plane protocol that is going to be mapped onto your GTPU header. That part we already have studied in the QoS part. I will introduce those core network related specs once. The PDU, SUPP, GTPU spec, and so on. I will introduce them once again. Again, SDAP also can have the parameters, um, and there is not much configurable from higher layer in the SDAP because it doesn't have any protocol header fields or anything which is required to be configured from RRC. Of course, SDAP entity will be established by RRC, but the parameters are not there. Okay. So that is 37,324 SDAP document. So all the material that is sent to you so far is a modified version of these whatever that could be found out in these specifications itself, or uh, presented in a presentable format. That's it. But every information comes from these specs. I did not invent anything, or I did not cook up anything on my own. Everything comes from here. Any questions related to these specs introduction? Because this is a repeated data, I did not ask you much for questions. Because just my idea is to introduce all these specs and show you where what is where, so that if you want to refer to them later point in time in your project environment, it would be useful for you. That's the idea behind this whole thing, whole exercise. Any questions? Anyone so far? All right.
Uh, I think FNAP and GTP also planning is energy.
Sir, I'm not getting your voice. It's getting broken.
No, I think I'm actually saying that FNAP and then EGTP also was planned.
Not getting it. Sorry.
Okay.
Sir, I
So
think he is
one
asking
said,
about the interfaces, F1 AP and all.
Sorry, what is it?
Sir is asking about the interfaces, I think, F1 AP and XNAP, I think.
We'll cover that.
F1AP
We'll cover
and
that in
F1.
the coming up sessions. We'll
Okay.
cover that.
Easy,
We did not yet
easy.
complete the. We have completed only up to radio part, and still RRC and NAS is pending. Today we'll start with RRC, but RRC is expected to be taken one more class on Monday. Also, we'll have to cover RRC only. Then we have to cover NAS. Idea is the time that is provided to me is to cover NAS plus X1, X2 AP plus S1 AP in single session. That is the kind of timeline I was given when this was planned. So I have to kind of stuff all of them in one single session and cover it up. But I will cover those things.
Okay.
X2 AP
But,
and
but EGTPU will be the, I think, endpoint, right? That's what actually I'm just, is there any plan for the EGTPU also?
which one?
EGTPU. EGTPU.
GTPU covered already.
Oh, okay. This is already covered.
GTPU done as part of QoS mapping itself. Yesterday itself we have finished it.
Okay.
GTPU we have covered. We have covered PDU, yes, session user plane protocol also we have covered. But NR
Okay.
protocol I have ignored because you guys did not ask for dual case carriers. So NR user plane protocol I have ignored. I did not cover that part. I have covered only PDU user plane session protocol.
Okay.
But I have covered along with GTPU, I have covered SDAP, SDAP plus GTPU plus PDUS UPP, I have covered together as a single unit in one class so
Okay.
that they will understand everything when they presented it all at once.
Okay. I hope NRUP also would be a better idea. Okay. But based on the timelines, we can.
But I was clearly told not to cover anything related to multiple times I was instructed about not to cover anything related to dual cases. And but the 17 days I have, I am hurrying up most of the times in covering the subject that is given to me itself. Okay, and
Okay.
I am fearing that I have to cut down some of the topics a little bit to complete this in 17 days because I was not given an extension to finish off it in a proper manner. Okay, but whatever
Okay.
that are important for these guys, I have elaborated them and I have spent most time on it. But whatever I thought they can actually learn on their own, or if I can give them reference points or something like that, with it they'll be able to pick up those topics I'm kind of ignoring. Okay, so I'm just introducing them and ignoring the rest of the part.
Okay, no
Okay,
issues. We can take care of that in our UP.
yeah, all right. Um, so we will take a break here for 15 minutes.